Hello everyone, how are you? I hope you can hear me. My audio is good and you can also see my screen. Good evening, Deepa Shri, Suryans, Abhishek, Shubham. Okay, so my audio is good. You all can hear me. Good evening, Amit, Punya. Okay, very nice. Thank you, Punya. Let's start. So today, I think you are all good with first law of thermodynamics. So first law of thermodynamics we have covered. You are not able to see PPT. Is everyone else able to see PPT? Okay. So Amit, maybe just refresh it. Okay. Refresh your side of Okay. So I hope you are all good with first law of thermodynamics. We have covered so many things. Whatever we have covered till now was first law of thermodynamics. Okay. So we have covered work transfer concept, heat transfer concept. We have covered first law of thermodynamics for closed system, for open system. In the open system, we have seen steady flow, unsteady flow, and we have done so many questions as well. Now you need to practice with more questions. Okay, go with any book, go with any previous year papers or something, and try to solve more and more questions for your practice. Okay. Today we are going to start new topic which is second law of thermodynamics. So we are going to one step ahead than first law and we going to enter into second law of thermodynamics. Good evening Abhishek. Okay, so let us start. So we are going to cover second law and Carnot theorem today. Carnot cycle, Carnot theorem. Okay. Okay. So now, before we go into second law of thermodynamics, we need to understand why do we even need second law of thermodynamics. Okay, so we had first law of thermodynamics, right? So what is the limitation of first law of thermodynamics? What does first law of thermodynamics doesn't tell you that we need to come up with the second law of thermodynamics. Okay, so there are three limitations of first law of thermodynamics. The first is it does not give you any idea about the direction of the process. It does not give you any idea about the feasibility of the process and the quality of the energy. What type of energy do you have? Okay, so we will see them one by one, each of them. Now, when we talk about direction, so direction means what? You see, look, you have a hot body. Let us say this body is at 100 degrees Celsius, and you have another body which is at T. This is T higher, this is T lower. It is at 30 degrees Celsius. Now, when these two bodies will come in contact with each other, okay, so you join them with a conductor or any body through which heat transfer can take place. So when they come in contact with each other, first law only tells you. So be very careful what I am saying. Each word is important. First law only tells you that if there is a temperature difference between two bodies, heat transfer will take place. That's all. So according to first law, we have two bodies and there is a temperature difference. Yes. Now there is a temperature difference. So first law is telling you there is a temperature difference. So heat transfer will take place. That's all. Now, in which direction it takes place, first law doesn't tell you. First law doesn't tell you in which direction it takes place. Simple. It is the second law that tells you that heat transfer always happens from high to low temperature. Always. It never happens from low to high temperature. Okay, never it happens that you bring a hot body and a cold body together and hot body become more warmer and the cold body becomes more cooler. No, always the hot body will become cooler and cold body will become warmer. Okay, so always whenever there is a temperature difference, heat transfer direction which is specified by the second law it tells you that heat transfer will always happen from high to low temperature. Okay, so first law of thermodynamics is not a directional law. It does not give you any idea about the direction of the process. According to first law, heat transfer will happen as long as there is a temperature difference. Okay, but in nature, what we have observed, that heat transfer always happens from high to low temperature naturally, I am saying. Okay, so it happens high to low temperature, and that is observed and explained by second law of thermodynamics. Okay, so this was the first limitation of first law. First law doesn't give you any idea about the direction of the process. Then second is feasibility of the process. Feasibility, what do you mean by feasibility? First law tells you whenever a process is happening, energy is conserved. Okay, whenever a process is happening, energy is conserved. Now if the process is happening or not, even if it is possible or not, first law is not going to tell you. For example, let us say you have this, voltage difference, and current is flowing, and because of this current flow there is some resistance, and this some losses, some electrical losses will be there, and this electrical energy will be converted into heat energy, q losses. Okay, at the resistance, what will happen? Electrical energy is going to be converted into heat energy. Now first law is telling you, when this process is happening, electrical energy, whatever electrical energy is going through this, right? Some electrical energy in form of current is going, some q losses are happening, and some electrical energy out will happen. So energy is consumed means what? Electrical energy in will be equal to electrical energy out plus Q losses. This is energy conservation. That's all. Energy in is equals to energy out. Okay. So first law is simply telling you that whenever a process is going to happen, energy will remain conserved. But now if you say that, if you say you have another circuit, okay, now you give some heat to it at the resistance, and current will flow, and there will be a voltage difference that will get developed. So in this process, still in this process, what is going to happen? Energy is conserved. But you tell me, is it possible? If you are, giving some heat at the resistance, will the current start flowing? No, right? So this process is not possible. This process of heat energy into electrical energy, conversion of heat energy into electrical energy, is not possible. Okay, but first law is not telling you this. First law is telling you, if this is happening, first law giving you no idea about the feasibility. It is just telling you that if this is going to happen, energy will remain conserved. That's all. If it is going to happen or not, first law will not give you any idea. Now it is the second law that will come and say that, later on we will see that if the entropy of the universe is less than zero, then the process is impossible. Process is infeasible or impossible. So first law gives you no idea. It is the second law that gives you entropy. It is entropy, I'm sorry, not es. Okay, so it is the second law that gives you some idea about the feasibility of the process. First law is simply the law of conservation of energy. It states energy will be conserved when a system undergoes a change of state or thermodynamic process. Okay, but it does not give you any idea if it is even possible or not. Clear? Yes or no? Less than, we will come to that. We will, Amit, we will understand entropy. Don't worry. One whole lecture is about entropy. I am just giving you a condition That second law is telling you if entropy of universe is less than zero, then this process is not going to happen. It is not feasible. Okay, so it is the condition that is given by second law. It is the second law that is giving you one condition that this process is not possible. But according to first law, it is possible. एंट्रोपी समझ में नहीं आता है. It's okay. We will try to understand it in the next lecture. Okay. Yes, direction I just told you, in the last slide, right, Sanjeev? This is not direction. This is direction. Okay. This is direction. Direction of energy transfer. Okay. This is the feasibility. Okay. Okay. No problem. Just see it. Just go back and see again. Okay. The recording. Now the third is quality. Quality of energy. What do you mean by quality? Quality is all the sources of energy have been divided into two types, high grade and low grade energy. Now, according to first law, you see, first law gave you one device that if you are giving some heat, it will give you some work, right? Q in, work out. So it gave you that summation of Q is equals to summation of W for a cycle, right? Now, according to first law, all the heat energy can be converted into mechanical or work energy. Okay? According to first law, all the heat energy can be converted into mechanical work or high grade energy. Okay, we will talk about high grade, low grade later on, but just simply understand that according to first law, all the heat energy can be converted into work energy. First law of thermodynamics does not talk about the quality, it only talks about the quantity. That if you have 100 units of heat, it can be converted into 100 units of work. It is the first law. That is the reason that first law is called as qualitative, is not a qualitative process. It is a quantitative process. So it discusses about the quantity of energy. Okay. According to first law, heat and work are of same equivalence. Now you see whatever what you have observed is you see any natural process. You see any natural process. For example, you have a bike and you put some fuel in this, right? Then it goes to the engine, and this engine you burn it. You burn the fuel, right? So fuel is converted into heat energy in the engine because of combustion. Now this heat energy pushes the piston, right? So this heat energy is converted into mechanical energy, right? But you see, you have a exhaust also attached. Now some flue gases that are going out, the flue gases that is going out of your exhaust pipe, they are at much higher temperature. You see, if the surrounding temperature is 30 degrees Celsius, these exhaust gases are around 50 or 60 degrees Celsius. Yes or no? Yes or no? So how did this exhaust gases reached at this higher temperature? Because of this heat energy. Because of this heat energy. Okay, that means this heat energy is not converted into mechanical energy completely. It is also lost. There is some heat lost because of exhaust. Also, you see your engine body is at higher temperature, right? It is very hot, so some heat will be going out from the engine as well. So heat energy is never completely converted into mechanical energy. There are always some losses that happens. Okay, so that is the reason we have defined heat energy as low grade energy and mechanical energy as mechanical energy, electrical energy, work energy, kinetic energy. These are all high grade energy. And what we have seen is that low grade energy can never be completely converted to high grade energy. Never be completely converted, but high grade energy can be completely converted into low grade energy. Now, for this example I have given you of the bike, okay, and there are so many examples. For example, power plant is also there. You are burning coal, right? You are burning coal, and you are converting that coal. I mean, you are burning fuel using that, right? Coal is burning, and some heat is generated. Now, by using that heat, either you are using it in a gas turbine or a steam turbine. So, but you see the exhaust pipes that is there, the chimney that you see in any power plant, that exhaust that goes out, it is at much higher temperature. Okay. So why did that exhaust gases are at very high temperature? Because they also absorbed heat from this fuel heat. So basically, you can never utilize heat energy completely. It must be converted into some losses will always be there. But you see, for example, you have this piston and it has some mass. Now you use some mechanical energy to push this piston inward. So what will happen? Sharp property which is creating difference between low grade energy and high energy. I'll tell you just 1 second. Okay. So, mechanical energy you are giving to push this piston inward. So, what will happen? Pressure and temperature will increase, right? Now, you leave this completely. You are not doing anything. So, whatever mechanical energy you have given to this piston will be, so this temperature will increase, and this temperature will slowly, when you stop, this will slowly come to surrounding temperature. If the outside is T infinite, it will eventually, Shivendra, wait for 1 second. Okay. So it will eventually come to T infinite. Why? Because it will slowly keep losing heat from the cylinder. So all this mechanical energy will be slowly converted into Q losses, and eventually your temperature inside the cylinder will be equal to your outside temperature. So all mechanical energy which is high grade energy can be completely converted into heat energy, but low grade energy can never be completely converted into high grade energy. Okay. So properties entropy. Okay. Abhishek, the property that distinguishes low grade energy into high grade energy is entropy. Okay, which we are going to talk about later on as well when we go to entropy. Okay. At the exit temperature will equal to exit calorie of, you can say, final temperature. Okay, finally, when you do some work on a system and you then leave it there. Okay, so when you work on the system, its property will change, right? And then you leave it there. Now eventually, after 5 minutes, after 10 minutes, 1 hour, or whatever, but eventually after some time, the system properties, temperature, pressure, and everything will be eventually equal to surrounding temperature and pressure. Why? Because it is continuously losing energy in the form of heat. So your all the mechanical energy will be converted into heat. Okay, got it? Okay, so Abhishek, that is entropy that distinguishes low grade energy into high grade energy. Okay, we'll talk about that when we go to entropy again. Shivender, you have to see that I am explaining something. Okay, so I cannot just go to first slide. Okay, so you have to wait for some time. Okay, so what do you want? What first slide? So this is first slide. Okay, limitation of laws of thermodynamics. First law of thermodynamics. Okay, let's move on. Okay, so we have discussed three limitations of first law of thermodynamics, and that is the reason. And again, this is basically entropy that explains this. And entropy comes in the second law of thermodynamics. So it is the second law of thermodynamics that explains all these phenomena. What? Direction of the process, feasibility of the process, and the quality of the energy. Quality of the energy. Okay. So, and most of them are basically explained through entropy. Okay, and entropy is a little complicated topic. So I would ask you to maybe, next session we will have next week for entropy, and I would ask you to just go through your notes, whatever you have studied in your bachelor's or engineering. Just go through it, try to understand it. But I will explain from the beginning, from the start, everything I'm going to explain, and I will like try to explain it from the best of my abilities. But if just give it a read, then it will be little easier for you. Okay. Today we are going to focus on second law and Carnot cycle. Okay. So before we go to second definition of second law or the statements of second law, I need you to understand what is the concept of thermal reservoir. So what is a reservoir? What is a reservoir? Can you tell me what is a reservoir? In general term, yes, huge container you can say. Yes. So basically a reservoir is something which has a huge quantity of something, and even if you are giving, for example, you have ocean or a sea. Now if you give water to that ocean, the quantity of water in the ocean is not going to change. It is not going to make any difference in that. Similarly, if you take some water from that ocean, again it is going to make no difference on the ocean, right? So it is a kind of reservoir. Similar to that, we have thermal reservoirs. So a thermal reservoir is a device, is a body that has a very large thermal heat capacity. What do you mean by heat capacity? Cp. Cp is the ability of the body to absorb heat or to reject heat without letting it change its temperature. Okay. So if a body has very high specific heat, that means whatever heat you keep giving to this body, its temperature is not going to change. Okay, its temperature is not going to change. Or even if you take heat from it, its temperature is not going to change. Okay, so basically no effect on temperature. So a thermal reservoir is a body that can supply heat, or it can also absorb as much amount of heat as you want without any change in its temperature. So more energy to increase 1 degree Celsius. It requires more energy to increase 1 degree Celsius. Yes, that is the definition. Okay. So basically, it is the amount of heat that you have to give. Okay. Or it is the amount of heat transfer that requires, that makes 1 degree Celsius temperature difference or something. Okay. But the physical significance is कि if a body has high specific heat, if you are giving it heat, basically heat transfer will not change the temperature. If a body has low specific heat, a little amount of heat transfer will change its temperature. Okay. So thermal reservoirs have a very large thermal heat capacity. That means that they are able to supply you heat, or they are able to absorb heat without any change in its temperature. Okay, so there is a source means it can supply energy in the form of heat without any change in its temperature, and sink is it can absorb energy in the form of heat without any change in its temperature. So the main point is, it whatever you are in, source can supply you heat without any temperature change, sink can absorb heat without any temperature change. Okay, so these are called thermal reservoirs. So now let us go to the first statement of second law. So there are two statements of second law of thermodynamics. The first is Kelvin Planck's, and the second is Clausius statement. So what does Kelvin Planck's statement tells you? It tells you it is impossible to develop a device that works on a thermodynamic cycle and produces work continuously while exchanging heat with a single reservoir. Okay. So what does it mean? What does it mean? It simply means it simply means that we have a device. You see, we have this heat exchanger, and it is giving you work output continuously with absorbing or while exchanging heat by a single reservoir. So it is exchanging heat from this source, it is absorbing, this device, this heat engine is absorbing heat Q1 and giving you work output. Now Kelvin Planck is telling you that this device is not possible. You see, it is impossible to develop a device. And this device is called as PMM2, Perpetual Motion Machine 2. So Perpetual Motion Machine 2 is a device that gives you continuous work output while absorbing heat from a single reservoir. Okay, so this source is a thermal reservoir, and this device, let me explain it one more time. Just be very focused. Okay, so heat engine, this is not heat engine, this is some device. Okay, let us not call it heat engine. This is some device that is continuously giving you work output while exchanging heat from a single reservoir. Okay, so it is absorbing heat Q1 and giving you work output. So if you do energy balance according to first law, if you apply first law here, first law, which is energy conservation, that is energy in is equals to energy out. So what is coming in? Q1 is coming in and W net is work output. So this is first law. So you see, first law is saying it is good. First law is saying it can work. But second law or Kelvin Planck statement of second law is telling you no, it is not possible. Why? Because we have always seen in nature that whenever heat transfer is converted into work transfer, there are always some losses. There are always some losses. Okay. So if this device is not possible, then what is possible? Then what is possible? So we have, you see, Kelvin Planck is saying that you cannot develop this device. What device? That exchanges or absorbs heat from a high temperature source and produces continuous work output. So Kelvin Planck is telling you this is not possible. But what is possible? Absorbing heat and producing some work, and the remaining amount of heat is lost to a low temperature sink, which is usually your surrounding, you see, in your bike, that fuel is converted to heat energy first due to combustion, and that heat energy is converted to, some part is converted to work output, mechanical work, and some is rejected to the atmosphere through the exhaust pipe or through the engine body, because engine body is also at high temperature. So the heat that is lost from that engine body is also going to the surrounding. Okay, so it is lost to the lower temperature. Okay, and this device that is absorbing heat from a high temperature, producing some work and rejecting some heat at low temperature is called as heat engine. Do you get this much? Yes, that is the limitation of first law. Okay, so first law is saying you can do this, but second law is telling you no, you cannot do this. Always there are some heat losses. And we have observed this. Okay, second law came because of observation. In our nature, we have, yes, Samarth, that is correct. There is no 100% efficiency, okay? Because there are always losses. This is basically telling you 100%, okay? Because efficiency is work desired output upon input, and it is equal, so it is 100%. But it is not possible, okay? It is not possible. It is not possible. Not possible because of second law, okay? So now, this is your heat engine. This is your heat engine. So they are work producing cycles. They receive heat from a high temperature source, converts part of heat into work, and reject rest of the heat to low temperature sink. To low temperature sink. Okay. So how do you define the efficiency of any work producing device? Yes, yes, that's what I am saying. No, but this is perpetual motion machine 2. And Kelvin Planck is telling you it is impossible. So PMM2 is impossible because it violates Kelvin Planck statement of second law of thermodynamics. Similarly, PMM1, now don't ask me what is PMM1, I have already explained this, is impossible because it violates which law? Which law? PMM1 violates which law? Yes, first law of thermodynamics. Okay? Chalo. So look, efficiency or any performance parameter is always defined as desired output upon required input. Always, this is the basic general definition. Required input. Okay. Now, heat engine is a work producing device. So what do you want? What is the desired output from a heat engine or a work producing device? What do you want from a work producing device? A work output? Yes. You want a net work output? Yes or no? So, desired output for a work producing device is net work. Okay. And in order to get this work output, what do you need to give? What is the required input? What is the required input? No, 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 no. Required input is Q1 or Q in. You cannot control Q2. Okay, you can only control Q1. This is what you need to give. That's all. You have no control on Q2. Now we can apply first law of thermodynamics. Look, when I said here that first law is not valid here, I mean, again, never say the sentence that first law is not valid. I am sorry. Okay, first law is always valid. First law is the law of nature. But basically, first law is a more generalized law. You can apply it anywhere. Okay. But second law puts an extra restriction on first law in terms of natural processes, in terms of real processes. Okay. So first law is the energy conservation law that is applied anywhere, even if something is possible or not possible. But it is the second law that puts an extra restriction on the first law to tell you that if this process is going to happen or not, if this heat transfer is going to happen or not. Okay, so never say first law is invalid. First law is always valid. So a device is only going to work, a heat engine or any device, any engine is only going to work when it satisfies first law of thermodynamics and second law of thermodynamics, both of them. Okay, now let's apply first law of thermodynamics, which is energy conservation law. So energy in is equals to energy out. I have applied first law of thermodynamics here. So what is energy in? Q1 is in. What is going out? Work is going out. Q2 is going out. So what is work? Work is equals to Q1 minus Q2. So I can also write Q1 minus Q2 upon Q1. I can also write 1 minus Q2 upon Q1. However, I want, I can write this. Okay. So this is your efficiency of heat engine. Yes. Okay. Now, next is Clausius statement. Next is Clausius statement. What do you mean by what does Clausius statement tells you? Now, Clausius statement tells you that it is impossible to develop a device that works on a thermodynamic cycle. Okay, so this is a thermodynamic cycle. This is a device that works on thermodynamic cycle and transfers heat from low temperature to high temperature without any external work. Means naturally or spontaneously. It simply means that you cannot develop a device that is thermodynamically possible, that can transfer heat, because you see this is your lower temperature, this is your higher temperature. Now this is a device that is transferring heat from a low temperature to high temperature naturally, spontaneously. Okay, so your Clausius statement is telling you that this device is not possible. You cannot naturally, whenever a hot body and cold body come in contact, the direction of heat transfer will be like this, not like this, not possible. Okay, so Clausius is telling you you cannot transfer heat from low temperature to high temperature naturally. So if this is not possible, then what is possible? So you see, you have a low temperature, you have a high temperature. Now, Clausius statement is telling you that you cannot transfer heat from low to high temperature. You cannot do this, right? But you cannot do this naturally. You cannot do this spontaneously. You can do this if you provide some external work input. So you see, you have refrigerator in your home. Okay, we will talk about this in a while. But basically, let's understand this. The Clausius statement is telling you that you cannot naturally or without any external work input, you cannot transfer heat from low to high temperature. So if this is not possible, what is possible? You transfer heat from low to high temperature, but with external work input. With this you can do this, with this you can do this. So based on this concept, based on Clausius statement, what are the devices that we have seen? Refrigerator in our homes, heat pump, all these, or air conditioning, all these works on Clausius statement. All these works on Clausius statement. Okay, so let us see. Refrigerator. So what does a refrigerator do? What does a refrigerator do? You see, this is your refrigerator in your home. Okay, and you have connected it to a electrical supply, electrical energy, right? So you are giving it some work input, electrical energy you are giving. Now tell me, what is the temperature inside your refrigerator? What is the temperature inside your refrigerator? Tell me quickly. Yeah, around 5. Very good. It's so here inside in your fridge, it is around 0 degrees Celsius or -1. But inside it's like 3 to 5 degree Celsius. Okay. And what is the surrounding temperature? Let us say 25 degrees Celsius. 25. Okay. Now you see, naturally what is going to happen? Naturally, in the nature, what is going to happen? You see, high temperature is this, low temperature is this. So naturally, some heat will always try to flow or leak inside the refrigerator. So this heat will try to raise the temperature inside the refrigerator. Now, what this refrigerator will do, it will continuously remove some amount of heat Q out so that it can maintain this temperature. It can maintain this temperature. Okay. So, refrigerator is the device that is continuously rejecting this heat out to maintain this temperature. And where is it rejecting? It is rejecting to the surrounding or the atmosphere. Okay. So this is your device. So this is your refrigerator. It is taking electrical energy and it want to maintain a lower temperature. It want to maintain a lower temperature. It want to maintain a lower temperature. In order to maintain a lower temperature, this refrigerator have to continuously remove this heat Q2 from this storage and supply this to the atmosphere at higher temperature. Atmosphere at high temperature. So this is your refrigerator. This is your body that you need to maintain at lower temperature. Or if, for example, your AC. Okay. So you want to maintain a room at lower temperature, for example, 20 degrees Celsius. So continuously that AC needs to remove this Q2, and where it is going to go? Of course, it is going to add to the surrounding, right? The atmosphere. So this is how. So the aim of refrigerator is to maintain a lower temperature than that of surrounding. The refrigerator is a device whose objective is to maintain a lower temperature than that of surrounding. Okay. So let us say, what is COP? COP, again, it is a performance parameter, so it will be desired output upon required input. Now, what do you want from this refrigerator? What is the desired output? Tell me quickly. What do you want? What is the desired output from this refrigerator? What is the objective of this refrigerator? So, what do you want from this refrigerator? Yes, maintain lower temperature. Okay, maintain T2. Yes, very nice. Maintain T2. Okay. Now, just 1 second. I'll. Okay. So, yeah. So basically, objective is to maintain lower temperature. Okay. And in order to maintain that lower temperature, this refrigerator has to remove this heat Q2 continuously. Whatever happens, it need to remove this heat Q2. However work you get, whatever is Q1 does not matter. What matters is if I need to maintain T2, I need to remove Q2. That's all. So basically, desired output is to remove Q2. And in order to remove this Q2, what do I need? What is the required input? What is the required input? Work input. Yes, work input. Okay. So now I can apply my first law of thermodynamics, which is energy in is equals to energy out. What is energy in? What is coming in? Q2 is coming in. What is coming in? Wn is coming in. What is going out? Q1 is going out. So Wn is equals to Q1 minus Q2. So I can write Q2 upon Q1 minus Q2. So always remember that here we have lower temperature in the numerator. Always remember, because the objective of refrigerator is to maintain lower temperature than surrounding. So always we have lower temperature in the numerator. In the numerator. Okay. Then the next application is heat pump. Okay, heat pump. What happens in a heat pump? You see, heat pump you use in winters in your home. Now in winters, what happens? You see, this is your room. Now in winters, the outside temperature is, let us say, 3 degrees Celsius. Okay, outside in winters, or 5 degree or 10 degree, whatever. I mean, whatever you want to assume. Let's say 10 degree. But 10 degree is not comfortable for you, right? So you want to maintain around, let's say, room temperature. You want to maintain 22 degrees Celsius. Okay. Now, what do? You install a heat pump. You install a heat pump here. And the purpose of this heat pump, now, first of all, you see, naturally, what is going to happen? Naturally, this is higher temperature, this is lower temperature. Now, naturally, heat transfer always happens from high to low temperature. So, there will be some heat that will be going out from the room. But you do not want that. Why? Because we want to maintain this temperature. If the heat is going out, temperature will reduce in the room, right? So what do you want? You continuously want to extract some heat from the environment. You in, you continuously want to extract heat from the environment to maintain a high temperature. You see, so what this heat pump is doing? Heat pump is absorbing heat from low temperature. Okay, so this is your low temperature. Heat pump is absorbing heat from low temperature and giving heat to high temperature room. Giving heat to high temperature room. So again, heat transfer is happening from low temperature to high temperature. Low to high temperature. Okay. So this is the concept of heat pump. Now, it looks similar to the refrigerator. The only difference is the purpose of heat pump, the objective of heat pump is to maintain higher temperature than surrounding. This time your surrounding is at lower temperature TL, and this is your room that you want to maintain at higher temperature. So this heat pump is continuously extracting heat Q2, and you need to give some work to it so that it can supply heat Q1. Now again, the purpose of heat pump is to maintain this T1. So no matter what happens, I need to supply this Q1. I do not care how much work I am taking. I do not care how much heat I am absorbing from low temperature. What I want is to simply supply Q1 no matter what happens. Okay. So if I want to define COP, which is again desired output upon required input, now you tell me what is my desired output? What is my desired output? Q1, yes, Q1. Required input is work input. Now I can again apply my first law of thermodynamics, which is energy conservation. Energy in is equals to energy out. So this is my device. What is coming in? Work input is coming in, Q2 is coming in, and what is going out? Q1. So work input is equals to Q1 minus Q2. So I can write Q1 upon Q1 minus Q2. So yes. Okay. So always remember that for heat pump, we take higher temperature. You see in the numerator, we have higher temperature. But in the refrigerator, we have lower temperature in the numerator. A lot of people remain confused later on. Okay, sir, what was in the numerator? I mean, what should I take for refrigerator? What should I take for heat pump? So that's why I want to clear it at this point of time itself. That refrigerator is a device that needs to maintain lower temperature. So here it is lower heat. Okay, and heat pump objective is to maintain a higher temperature, so you take higher heat transfer QH. Okay, is it clear? Is this much clear to you? Okay. Okay, let's move on then. So what is the relationship between COP of heat pump and COP of refrigerator? So you see, what is COP of heat pump? Higher temperature, so higher means Q1 upon Q1 minus Q2. This is your heat pump COP. Now let me do minus 1 plus 1 here. So if I do that, I will get Q1 minus Q1 plus Q2 upon Q1 minus Q2 plus 1. Okay, so now I can remove that. So I have Q2 upon Q1 minus Q2 plus 1. Now tell me what is this? Tell me what is this? Yes, yes. This is COP of refrigerator plus 1 is equals to COP of heat pump. Okay, so this is the relationship. Directly you can get an objective question from it. You can get a direct objective question on this. They will give you COP of heat pump. You need to find out COP of refrigerator or vice versa. Okay. What is the relationship between efficiency and COP of heat pump? So, efficiency of heat engine was what? Work output upon Q in. So, it was Q1 minus Q2 upon Q1. Now what can I do? Let me take it here like Q1 upon Q1 minus Q2. Now what is this? Yes, Shivendra, just 1 second. What is this? COP of what? Heat pump. Yes, 1 upon COP of heat pump. So this is a relationship between efficiency of heat exchanger, heat engine to the COP of heat pump. Okay. Take it, Shivendra Raj. Who was asking me for? Yeah, Shivendra Raj. Okay. No, Punya, be very clear about COP formula. Okay. Chalo. Now, what is the relationship between efficiency of heat engine and COP of refrigerator? So you can derive it separately, but already we know that efficiency of heat engine is equals to COP of heat pump, and we also know that COP of heat pump is equals to COP of refrigerator plus 1. Okay, and we can derive it also from the formula. So whatever you want to, you can do, but basically this is the relationship between efficiency and COP of heat engine. Okay, got it? Pretty simple, and you can get objective question from it. Okay. Yeah, there is nothing to explain here. What is, it's simple. You bring this in the denominator. You bring this in the denominator. That's all. And this is basically your COP of heat pump. Simple mathematics. There is no concept here. Okay. So should we move on? Okay. So these were the statements of second law, which is very important. You surely get one or two questions from either heat engine or refrigerator or heat pump. Something sometimes you will get. Okay. Now let us move on to Carnot cycle. Carnot cycle. Okay. So Carnot cycle is an ideal hypothetical cycle in which all the processes are reversible. So all the processes are reversible, and that is why it is called as a reversible cycle. Now there are four processes. What are the four processes? One is reversible adiabatic compression. One is reversible isothermal heat addition. Then one is reversible adiabatic expansion and reversible isothermal heat rejection. So in simple terms, if you want me, I can say there are two isentropic process. Isentropic means reversible adiabatic, okay? And we have two isothermal process. Okay, so isothermal are heat addition and heat rejection, and isentropic is expansion and compression. Always expansion and compression are isentropic. Always they are isentropic. Okay. Now let us try to understand these processes. So if we say that what is a reversible adiabatic compression process looks like. Okay. Reversible adiabatic compression process looks like. So when I say isentropic process, it simply means that entropy, later on again we will see that later on. Okay, so ds, this formula we will drive next in the next session, dq by t. Okay, no, not no losses, it simply means that no irreversible losses. Okay, no friction losses, no entropy losses basically. Okay, there could be other losses. Okay, so reversible adiabatic, no entropy losses basically. Okay, so this is entropy, ds is equals to dq by t. Okay, so it is actually saying, that first of all, you see what we have a compression process, so as soon as I said that the compression is happening, I know. So you see, first of all piston is here, and now I am compressing it. So in this, volume is decreased, but of course pressure will be increased. Yes, so in this process pressure increases, volume decreases, and entropy is constant because it is isentropic process. What do? Is we insulate our, it is the same device. Okay, I am just explaining the process. Okay, so we insulate it perfectly. So dq, we become dq is equals to 0. If dq is 0, so if this is 0, ds is 0. Okay, ds is 0. So basically entropy, we keep constant, we keep entropy as constant, and because pressure is increasing, temperature is also going to increase. Okay, because pv is equals to mrt, so temperature is going to increase, pressure and temperature both are going to increase. Okay, now next is reversible isothermal heat addition. Now what we are doing is we are adding heat, we are adding some heat in such a way that the temperature is not increasing, okay, so we are doing it very 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 slow. Okay, so we are doing it very very slow, we are not letting the temperature to increase. Okay, so now intentionally it is a isothermal process, that means temperature will remain constant. Now when we are adding heat, so piston is going to move up. Piston was here earlier. Okay, after this you come here. Okay, so piston is here, now you add heat, so piston is going to move up. When piston is moving up, pressure will reduce and volume will increase. So pressure decreases, volume increases in this process, and temperature remains constant. Now what do we have? ds is equals to dq by t. Now we are adding heat, that means numerator is increasing while the denominator is constant. That means entropy is also going to increase. Okay, so mark these processes. In reversible adiabatic, pressure is increasing volume is decreasing, temperature is also increasing, but because it is isentropic process, so it is constant. Then iso reversible isothermal heat addition, you are adding heat, so piston is going up, volume increases, pressure decreases, temperature we are keeping constant intentionally, okay, and dq increases, so entropy also increases, okay. Then after this, then we come to this. Now after this, we do expansion. Now we stop giving heat. Now we stop here, we were giving heat, right? Then when piston reaches here, we stopped giving heat. So if we stop giving heat, but still the expansion is happening, still the piston is going up. So further pressure decreases, volume increases. But now it is isentropic, so there is no heat. So dq by t, no heat, that means ds is also zero, so entropy is constant, pressure decreases, so temperature also decreases, and volume increases. You see volume is increasing here. Now finally we have reversible isothermal heat rejection process, heat rejection. So now you are rejecting heat. You are rejecting heat in with a constant temperature. So temperature will remain constant. You are not letting the temperature increase. You are moving piston very, very infinitely slowly. Okay. So now again, when the piston is now when you're removing heat, piston will come down. Okay. So from here we go here, then here. Now piston will go down. So now again pressure is increasing, volume is decreasing. Okay, so pressure is increasing, volume is decreasing, and again ds is equals to dq by t. Now denominator is constant, numerator decreases, so entropy also decreases. So do you are you able to imagine how pressure, temperature, and volume are changing in all these four processes? It is just to give you a visualization of what is happening. Okay, piston is going up, so pressure is reducing because volume is increasing. Okay, piston is going down, so volume is increasing, volume pressure is increasing, volume is decreasing. Okay, now combined all these four processes, we define our Carnot cycle. Okay, so 1 to 2 is reversible adiabatic compression. So you see this is isentropic compression, isentropic compression that is happening here, 1 to 2. Okay, now 2 to 3, what are we doing? 2 to 3 is reversible isothermal. You are adding heat, heat addition. And then when you have added heat, then it goes to turbine, and here it is reversible adiabatic expansion. So isothermal expansion, and then finally heat is rejected, so it is reversible isothermal heat rejection, reversible isothermal heat rejection. Okay, so these are the four processes that are happening here. Okay, so first of all, gas is compressed here in 1 to 2, then you will add heat to the gas, then gas is expanded, you take work output from it, and then eventually it is rejected to the heat is rejected to the heat sink. Okay, so this is how your Carnot cycle may look like. Okay, now let's go to PV and TS diagram. PV and TS diagram. So Now, let us say this is my PV diagram and this is my TS diagram. So drawing TS diagram, it is possible to add heat simultaneously, temperature will not increase. Abhishek, we will come to that, don't worry. Okay, just give me 2 minutes. Next, we will come on that. Okay, just to give the answer, I will tell you that temperature always changes. Isothermal process in reality is never possible. Okay, so yes, temperature increase, yes. Okay, chalo. So temperature entropy diagram is very easy. First of all, 1 to 2 is temperature increases, entropy constant. So if entropy is constant, if entropy is constant, so how can I draw this? If entropy is constant, temperature is increasing on TS diagram, vertical line, yes. So this is 1 to 2. You see, your entropy is same, S1 is equals to S2, but your temperature increases from T1 to T2, right? Now, 2 to 3. How can I draw 2 to 3? Here temperature is constant, entropy increases. How can I draw horizontal line? Yes, very nice. So, I can draw horizontal line. Okay, 2 to 3. Now you see here, temperature is constant at T2, so T2 is equals to T3, but your entropy is increased to S3. Again, 3 to 4. How can I draw? Temperature decreases, entropy constant. Vertical line downwards, okay? So, this 4. Okay, so again you can see C3 is equals to C4, but my temperature is decreased to T4. Okay, and also finally temperature is constant and entropy decreases. So I already know that you all know this, that I would have to draw it like this. Okay, so this is my TS diagram. Okay, so this is basically isentropic compression. So this is work input. This is isothermal heat addition, Q in. This is isentropic expansion, work output. And this is isothermal heat rejection. So Q out. Okay. Now let us come to PV diagram. Let us come to PV diagram. So 1 to 2. It is isentropic processes. Now again go back to the basics. I have shown you all the diagrams: constant pressure, constant volume, isothermal, adiabatic, polytropic on the PV diagram. Yes or no? I have shown you all the diagrams. How to draw processes on the PV diagram. Yes, if you have revised, you may remember. Okay, so do we know that the slope of isothermal curve is less than slope of, do you remember this, adiabatic? Because you see, PVK is equals to constant was the general equation. Now for isothermal, K was 1. For adiabatic, K was 1.4. Do you all remember this discussion we had? Yes. Where are other people? Do you all remember that this discussion? Have you revised? Okay, nice. Nice to see yes there. Okay, so remember this slope of isothermal process or curve is less than slope of adiabatic. Okay, so the first process is reversible adiabatic. That means isentropic compression. So in compression, volume is going to decrease and pressure is going to increase. So I know it will be a curve, right? I know it will be a curve, and in such a way that volume is decreasing. So if I start from here and if I draw something like this, so can you see that you see your volume is decreased? Your volume was V1, now your volume is V2, right? And your pressure is increased from P1 to P2. Do we agree with this? You see, pressure is increasing, volume is decreasing. Yes. Now, the next process is isothermal heat addition. So, it is an isothermal process in such a way that pressure is decreasing and volume is increasing. Okay. So, can I draw it? Just let me know if you agree with me. Can how I should confuse you? Okay. So, can I draw it? Hmm, like this or like this? First, second. Which one is isothermal? First or second? Yes, first, because you see, second has a higher slope. Second has a higher slope. First has a lesser slope. Closer to x-axis means lesser slope. Closer to y-axis means higher slope. Okay. So let me rub everything. So isothermal process I can draw with a lesser slope such that pressure is decreasing, volume increasing. So if I draw something like this, okay, something like this. Now, in fact, wait. Okay. Now, if I draw something like this, okay. So now you see, your pressure is decreased to P3, right? Pressure is decreased to P3 and this is 2 to 3, right? 1 to 2 and this is 3. So and your volume is increased to V3. Yes, so it makes sense. Now the next process is isentropic expansion. Isentropic expansion. So here also pressure is decreasing, volume is increasing. So can I draw something like this? So you see, your pressure is decreasing to P4 and your volume is increased to V4. Yes, satisfy the condition, and slope is also higher. Yes, yes or no? And finally, it is isothermal heat rejection. So now the pressure is increasing, volume is decreasing. So pressure is going to increase, pressure is going to increase, and volume is going to decrease. So if I draw this, I can say that the pressure is reduced. You see, pressure is reduced to P1 and the volume is reduced to V1 from V4. Okay. So this is my PV diagram. Again, this is Yes, Amit. Any doubt? You have raised hands. This is my isentropic compression. This is my isothermal heat addition. This is my isentropic expansion, work output. And Q out, this is my isentropic heat rejection. Okay. Now I know it could be little complicated at the first time, but if you revise and you go step by step how I have defined it for you, and if you revise it once or twice, it will be clear. Are we okay? Yes, sorry, isothermal. Yes, thank you. Thank you, thank you. My mistake. It is isothermal heat rejection. Thank you. Okay. Chalo. So this Carnot cycle is very important. Okay, they in terms of that we utilize it in reference for other cycles. This is the cycle that will always give you the maximum efficiency or maximum work output. Okay. Now the question is why Carnot cycle is an ideal cycle and not a real cycle. You see, Carnot cycle is never utilized in reality. Why can't we make the cycle real? Why can't we realize this Carnot cycle? Okay, because there are two reasons. There are two reasons, and here I will answer Abhishek's question that you see 1 to 2. Let's say 1 to 2 is reversible adiabatic compression. So basically, you are doing compression, yes. Now, this compression you have to do in such a way that there is no heat transfer. Okay, adiabatic means what? No heat transfer. Now, in order to have no heat transfer, basically temperature difference will be zero. So you see, heat transfer happens when, for example, you touch a hot plate, right? Now, in order to check how hot the plate is, you do not just keep touching it. You just touch it and remove your hand. Okay? Because the more amount of time you give touching that plate, the more heat transfer happens. Yes? Amit, why are you raising hand again and again? Okay. So the more amount of time you give for heat transfer, the more heat transfer happens. So basically, heat transfer requires time, right? Now, if we do our processes as fast as possible, like at infinite speed, that we do not allow any time for heat transfer. You see, we are doing we are doing our process at an infinite speed so that we are not allowing any time for heat transfer, and that is the way we can achieve a adiabatic process. Okay, so basically adiabatic process should be done at very 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 high speed or in a very fast way. Okay, chalo ठीक है. Somehow you have achieved the adiabatic process, somehow you have achieved a adiabatic process. Now you have reached here. Now you have reached here at point 2. Now 2 to 3 is a isothermal process. Isothermal process. Okay. An isothermal heat addition, let us say. Now you see, how can you achieve a isothermal process? You can, like you can try to remove heat side by side. Okay. You can design your engine in such a way that whatever heat is entering, it is some part will be utilized to raise the pressure, and some part will try to raise the temperature. Now the part that is utilized to raise the temperature, so you can use some coolant around the engine or that body to cool that uh, body, to cool that engine. Okay, So basically, you can surround your engine by a coolant or something, so that whenever temperature increases, this coolant this take this heat and it will not allow the temperature increase. This is one way. But there is one more thing. You see, if we have an engine and there is a piston and cylinder arrangement, okay, or any engine, any any powered producing device or power consuming device, whatever it is, there are always moving parts. There are always moving parts, okay. And wherever there is a motion between two bodies, wherever there is a relative motion between two bodies, there will be friction. Friction is something that you can never remove. You can reduce it. You can reduce friction by using lubrication, by using other things, okay. But you can never eliminate friction. You can never reduce it to zero. So friction will always be there. When friction is there, so what happens because of friction? Heat is generated. If heat is generated, then temperature is going to increase. Okay, so friction will always come into play and it will increase the temperature no matter what you do, no matter what you do. Okay, so now what can you do? What can you do to so that friction will not be there? So you can move your piston at infinitely slow speed, at very slow. You see, more the speed, more the friction, right? So you reduce the speed of your piston to infinitely slow speeds at a very slow speed so that it will not allow any friction. So basically, in order to achieve isothermal process, your process will be very slow. Okay. So now what are we talking here? We are saying that 1 to 2 is very fast. This is very fast. And then 2 to 3 is very slow. Now you see the combination of these processes are not possible. First of all, getting an isothermal process in itself is not possible. Okay, because friction will always be there. You can achieve all the processes. You can achieve isochloric process. You can achieve isobaric process. You can even achieve sometimes adiabatic. Like if your insulation is so perfect, sometimes you can achieve adiabatic. Although adiabatic is also very difficult, okay, but there is no way that you can get a isothermal process, and that is also third law of thermodynamics, which we are going to see, that continual motion of two bodies without friction is not possible. So friction will always be there, okay, and therefore you can never achieve isothermal process. So isothermal process in itself you can't achieve. Then the combination of adiabatic and isothermal is not at all possible because one process is very fast, one process is very slow. So basically, you see, here you have to be very slow at this point. As soon as you enter here, you have to be very slow. So that you have to reduce your speed from here itself. You cannot just reduce your speed to zero at an instant, right? You have to start slowing down from a distance. Now, as soon as you slow down, you will get some time for heat transfer, right? So then it is not adiabatic. Then this process is not adiabatic if heat transfer happens. Also, let's say you stop here, you slow down here. So, I mean, you started slowing down here. That means that here it will have some speed. That means here it will have some friction. So isothermal will get distracted. So basically, the combination of adiabatic and isothermal process clubbed together is impossible to achieve. Okay, so that is why Carnot cycle is an impossible cycle. It is an ideal cycle. You want to design a heat engine that will be so close, not a heat engine, any power producing, any power plant, anything, any power producing device, it should be as close to Carnot cycle as possible. But still you can never achieve Carnot cycle. It is not possible. It is, you cannot do that. Okay, that is why it is an ideal cycle and not a real cycle. Okay, So isothermal process can be achieved only if the piston moves very slowly to allow heat transfer so that the temperature remains constant. Adiabatic remains can be achieved very fast. So whatever I have told you, I have written here. You can take a read as well. Okay, chalo. Let's move on. So is it clear till now? First of all, whatever we have discussed here, is it clear to you? Yes, yes. Which one? This one? Shivendra Raj, I think you're very. I think you are the only one I get request to get the screenshots. I mean, I don't know, you may have a different way of studying, but I do not understand why you want to take a screenshot when you get the PPTs anyway. ठीक है, it's fine. I mean, I'm not complaining. It just I do not understand the logic behind it. It's fine. Everyone have their own way of doing things. So okay. So do we move ahead? Okay. Let's move ahead. Now, so so I hope it is clear whatever we have discussed. Now let us try to discuss a little bit about Carnot cycle, how to define its efficiency. So efficiency of a heat engine that we have already discussed is QL upon lower heat upon higher heat. This is lower heat. This is QL. This is QH. Okay. Now, what are these? These both are isothermal process. Yes. Yes. And if you remember, heat transfer. Okay, okay, it's okay. I mean, Shivan Raj, it's fine. I mean, it's you have your own style, so it's fine. I mean, I'm not complaining. I'm just observing. I mean, I just said what I observed. Okay, so heat transfer for a isothermal process. I hope you remember the equations. I have very beautifully, given you a summary of everything. So still, if you don't remember, it's not my fault. Okay, isothermal process. So it was dq is equals to dw is equals to mrt ln p initial by p final. That was isothermal process. Okay. So if I talk about process 223, so that is q in or qh is equals to mr t higher. If this is, let us say, t higher, and this is what, t lower. Okay, t higher ln initial pressure is p2, final pressure is p3. Yes. What about 4 to 1? 4 to 1. So it is q out is equals to q lower. Now it is going out. You see, it is going out. So it will be minus mr t lower p initial. Initial is what? P4 by P1. Now let me remove the minus and I can write ln P1 by P4. Okay. Now, okay. Now, you see, what are these processes? Now, what are these processes? These are isentropic processes. And I hope you still remember the ideal gas equations for all the processes. So Isentropic process, what was it? If I take process 1 to 2, can I say, which is what? Isentropic compression, yes. So can I say T2 by T1 is equals to P2 by P1 gamma minus 1 by gamma? Yes. How about process 3 to 4? It is also isentropic. Can I say T3 by T4 is equals to P3 by P4 gamma minus 1 by gamma? Yes. Now you see, look, T2 is equals to T3. If you see the diagram, T2 is equals to T3 is equals to TH, and T4 is equals to T1 is equals to TL. Okay. So can I say T this T2 is equals to TH by T1 is TL is equals to this, and T3 is again TH upon TL. Okay, so can I say TH by TL is equals to P2 by P1 gamma minus 1 by gamma is equals to P3 by P4 gamma minus 1 by gamma, because all are same. Yes. So if I take these two equations, so I can simply cancel this, and I will get P2 by P1 is equals to P3 by P4. Okay. Now, if I bring back this equation, what can I write? Efficiency 1 minus QL by QH. So what is QL? This is QL, okay? 1 minus MRTL ln P1 by P4, and it is MRTH ln P2 by P3. So can I, rearrange this and say P2 by P3 is equals to P1 by P4? Just rearrange. P1 goes here, P3 comes here. That's all. Okay. So P2 by P3 is equals to P1 by P4. So simply I can cancel this. I can cancel this. And efficiency is equals to 1 minus QL by QH is equals to 1 minus TL by TH. Okay. Now this, by this I can write QL by QH is equals to TL by TH. Okay. So it's very important to understand here is that for a reversible cycle or Carnot cycle, always try to use 1 minus TL by TS. This is the equation you should use for reversible. Okay. And because QL by QH is equals to TL by TH. Now, for if in the question they have not given Carnot cycle or reversible cycle or Carnot engine, then you will use a general formula that we derived earlier, QL by QH. So this can be used anywhere. This is used for reversible or Carnot engine. Okay, got it? We have just defined this. Any doubt? So, so now what is the effect of temp T1 and T2 on efficiency of Carnot cycle. So you see, let's say you have this Carnot engine or reversible heat engine. This temperature, higher temperature is 350 Kelvin, T higher. T lower is 300 Kelvin. Q2, Q1 work output. Okay. Now what is the efficiency of Carnot cycle? 1 minus T lower upon T higher. Okay. So 1 minus 300 by 350. So if you solve this, you will get 14.28%. 14.28%. Okay. Now let us say what you do first. Let's increase the source temperature. Source temperature, which is what? TH. And let us say take a 400 Kelvin. Okay. So now 1 minus TL by TH, 1 minus 300 by 400. So if you solve this, you will get 25%. 25%. Okay. Now, secondly, let us try to decrease the sink temperature. So T lower is equals to, let us decrease it by 50 degrees Celsius. Okay. So efficiency is equals to 1 minus T lower upon T higher, 250 upon 350. So it is 28.5%. Okay. So what can you conclude with this? Can you give me one conclusion by seeing these three figures? These three figures. Can you give me some conclusion? What have you understood by decreasing sink temperature gives more efficiency than? Yes, that is absolutely correct. Increase of source and decrease of sink temperature. Yeah, that is also true. But better observation is that you have two ways of increasing efficiency. First is increasing the higher temperature. Second is decreasing the lower temperature. Now this process is more effective because you have a higher efficiency increase. And also it's much easier because you see, working at very high temperatures is basically requires more, more resources. And in order to maintain that temperature also, so if you are maintaining something at this temperature, or let us say 500 Kelvin, the losses that will happen at this will be much higher. Okay. So what we have understood is that the most effective way, the most effective way to increase the efficiency of the reversible heat engine is to decrease. I mean, both ways efficiency is increasing, but this is more effective. Decrease the sink temperature or decrease the temperature of heat rejection. Now, Then why don't you just keep decreasing the temperature? Why don't you just take the minimum temperature that is possible? What is the limitation? Can you tell me? Why can't you just keep decreasing the temperature if the efficiency is so high? Because, any idea, anyone? Because there is a restriction, you see. There is a restriction. You cannot work below restricted by atmospheric temperature. So if you are working below atmosphere, for example, your atmosphere is 30 degrees Celsius, and you want to and you have already maintained 20-degree here, then you cannot reject heat. Why? Because naturally heat will flow inside. Okay, so this temperature should be greater than surrounding or atmospheric temperature. Otherwise, you cannot reject heat. So the minimum temperature, what we assume here is surrounding temperature, or mostly we assume surrounding temperature. Okay. Yes. Any thoughts? Any questions? Yes, you. That is what I am telling you. That you always try to maintain lower temperature at sink. Basically, you want to reject heat at the lowest temperature possible. But what is that lowest temperature? It is the surrounding temperature. So always you reject to surrounding. The example I gave you in the beginning of that bike, that exhaust gases, they are rejected to the surrounding, right? That when your engine heats up, the heat is lost to what? The surrounding. Even in power plants, the exhaust gases are exhausted to the surrounding, right? So basically, your sink temperature, your surrounding is your sink itself. Okay, like if you see what is your sink in your practical applications, it's the atmosphere, it's the surrounding only. Okay, so basically, your sink temperature should always be greater or equal to the surrounding temperature. You cannot reduce the temperature below the surrounding. Otherwise, what will happen? Heat will start flowing inside the system from the surrounding. Okay, this case, if you already maintain sink temperature 20-degree and outside is 30, then start heat will start flowing inside. That is not you want. You want to reject this. Okay, got it? Chalo. So what about COP of heat pump and refrigerator? So COP again. So what was COP of refrigerator? It was, what was in the numerator, lower or higher temperature? What was in the numerator, lower temperature or higher? Lower heat or higher heat? Quickly. Yes. This much time people have taken to answer this seriously. When I focused on that particularly, Q lower upon Q higher minus Q lower. Okay. So this is for normal heat engine. This is not ideal. This is any refrigerator. But COP of a Carnot refrigerator for a reversible refrigerator is T lower upon T higher minus T lower. Okay. Similarly, COP of heat pump. Now I think you should get this. This is Q higher upon Q higher minus Q lower. But COP, this is for actual one, okay? Now for Carnot heat pump is T higher upon T higher minus T lower. So you see, here the denominator is same. You see, denominator is same. Only difference is numerator. So here we have higher, here we have lower. Okay? And these formulas are only applicable for Carnot or reversible refrigerator. This is reversible heat pump. So the temperature form of these formulas are only valid for reversible devices. Okay? Got it? Yes? Okay. So Carnot theorem, basically there are two theorems. Okay, there is a little derivation and some sort of this is there, but we are not doing that because it's not necessary. Okay, it's not required also. So Carnot theorem is telling you, it says basically that all heat engines operating between the given constant temperature source and a given constant temperature sink, none has a higher efficiency than a reversible engine. So basically, let's say you have T1, T2 work output. This is engine 1, and you have T1, engine 2, T2 work output. Okay, so whatever engines are there, if they are working between same temperature limits, same temperature difference, then always and always reversible or Carnot heat engine will give you the maximum efficiency. Okay, reversible engine will give you the higher efficiency if the temperature difference must be same for all the engines. You take 10 of these, you take 10 of these engines, as long as the temperature difference is same, reversible heat engine will give you the maximum efficiency. Okay, then Carnot theorem 2 says the efficiency of all reversible heat engines operating between same temperature levels are same. So basically, if you have more than one reversible engine and the temperature difference is same, you see temperature difference of all the reversible heat engines are same, then all of them will give you the same efficiency. All of them will give you the same efficiency, and then that efficiency will be maximum for that given temperature range. Yes. So the point to be noted here is that reversible engine will give you first of all the maximum efficiency if the temperature limit is fixed. Then if the temperature limit is fixed and you have multiple reversible heat engines, then their efficiency will remain same. Their efficiency will remain same. It will only depend. You see what we have defined, right? Efficiency of Carnot engine is T1 minus T2 upon T1, right? So it is only dependent on temperature. That's all. It is not dependent on what fluid you are using. You are using gas, you are using water, you are using steam, whatever you are using, it does not matter. It is only depend on temperature. It only depends on temperature. That's all. It is a function of temperature only. Yes, temperature difference or temperature ratio of temperature. It's basically ratio, no? 1 minus T2 by T1, right? So ratio you can say, but you can little modify that equation that we defined earlier. Okay, Q1 by Q2. It is temperature. It will basically it is a function of temperature only. It is a function of temperature only. That's all. It does not depend on the working fluid. It does not depend upon you are using water, air. Okay, you're not uh, whatever working fluid you are using. It is independent on that. It is only depending upon the temperature. So the efficiency of the reversible engine is independent of the nature or amount of the working substance undergoing the cycle. Undergoing the cycle. Okay. So I hope. Okay. So this is it. This is what I, because now we have to move on to another topic called entropy. It was not possible to start entropy today, so I only covered. So this is also a major section. Okay. So we have covered second law of thermodynamics, the statements of second law of thermodynamics, and Carnot efficiency, Carnot theorem, Carnot engine. Itself change in entropy will zero if the adiabatic process, then why we need to put extra term irreversible is according to change in entropy formula. If dq is zero, then it itself change in entropy will be zero. That is isentropic, right? If it is adiabatic process. Okay, I get what you are saying. Okay, so I will tell you this when we study entropy, but just to give you some idea, adiabatic process, look, reversible adiabatic process is always isentropic, but isentropic process is not always reversible adiabatic. It can be some other process which is irreversible process as well. Okay, it may not be adiabatic. It may not be adiabatic. So reversible adiabatic process is isentropic process, but isentropic process यानी कि entropy can be zero in many ways. Not only, yes, Abhishek, that is right. 300 and 310 will give the same efficiency. Yes. Why it may not be adiabatic if dq is equals to 0? No. Wait. Look, ds is equals to dq by t plus there is some other term called this. Okay, let's not go there at this point of time. When we cover entropy, then if you have doubt, then we can discuss this. But entropy generation for reversible is zero only. Okay, so we will talk about this, don't worry about this. Okay, so there could be other cases when entropy is zero, which is in irreversible processes it may happen. Okay, so this is the whole term actually. ds is equals to dq by t plus entropy generation. This is the whole formula. This is we use for reversible only. This term comes up play when irreversible process is there. Okay, so don't worry about that. Limitation of first law. Okay, wait. So we will take this when we study entropy. Okay, everything will cover there. Okay, so Shivendra, I'll explain it very brief. Okay, the first thing was there are three limitations. Okay, three limitations. The first is direction. First law does not give you any idea about the direction. Second is feasibility. If the process is feasible or not, it does not give you any idea. And the quality. So when we talk about direction, direction means first law tells you, just to give you an example, first law tells you that whenever there is a temperature difference, heat transfer will happen. That's all. So wherever there is a temperature difference, heat transfer will happen. That is the first law that is telling you. It is not telling you that heat transfer will happen from high temperature to low temperature. But that is what we have observed in nature. What we have observed, that whenever we bring a hot body and a cold body, heat transfer always happens from high to low temperature naturally. Yes, but first law gives you no idea. It tells you temperature difference means heat transfer. It is the second law that gives you that there is a direction of heat transfer. It always happens from high to low temperature, which we also have seen in our Clausius statement. Okay, so that is a direction thing. Yes, that's what I am trying to say. Okay, so it simply tells you that temperature difference is there, heat transfer will happen. That's all. Okay, then about feasibility is basically it tells you that whenever some process is going to happen, whenever some process is going to happen, energy will remain conserved. Now, if the process is going to happen or not, first law is not going to tell you. First law is telling you always energy is conserved. Process is going to happen, process is not going to happen. Hypothetical process you do, but whatever process is going to happen, energy will remain conserved. It does not give you any idea about if the process is going to happen or not. Now it is the second law that tells you that yes, it tells you possibility. Okay, feasibility means possibility. If the process is even possible or not. Okay, so now second law comes in and it gives you some condition in terms of entropy and tells you if this condition is satisfied, then only this process is possible. Otherwise, it is not possible. So the feasibility is explained by second law, not the first law. First law says process happens, energy is conserved. Now, if the process happen or not, I don't know. Okay, if this thing is going to happen, then the energy will remain conserved. I don't know if it is going to happen or not. Okay, and finally, what we have seen is quality. So quality means what? This is what we have studied in first law, right? So first law was saying net heat transfer is equals to net work transfer. Again, it is energy conservation, right? Whatever energy, whatever net heat is going in will be equal to net work transfer. But what we have seen is in nature that not all the heat is converted to mechanical work or work, right? What we have seen is that whenever heat is converted to work, there are always accompanied losses. Always losses is going to happen. Whenever, look, simple case I will tell you, whenever heat transfer will happen, the temperature of the body will rise up. And whenever temperature of the body will rise up, it will lose some heat to the surrounding because there is a temperature difference between the body and the surrounding. So that heat is not utilized, it is just lost. You can't do anything. That means that complete heat will not get converted into work, but it will be converted into work plus some losses. Okay. So there we have learned the concept of high grade energy and low grade energy. So low grade energy, which is heat, cannot be completely converted into work, which is a high grade energy. Work, mechanical energy, kinetic energy, electrical energy, potential energy, these are all high grade energy. Okay. Now, high grade energy can be completely converted into work, which I have also given an example. If you have not seen today in the lecture, you can see in the recordings. Okay, just go through the first 10-15 minutes, you will get some idea. Okay, got it? Okay, chalo. So I think we are done here for today. I will see you on next week sometime and we'll start entropy. Then we will have the numerical session for both of them, second law and entropy together. Okay. Again, I would ask you to revise entropy before we start the entropy session. Revise the entropy session, entropy topic, so that like it will be get easier. You will not get confused on small things. Okay, chalo. I'll end this session. Thank you so much. Thank you, Punya, Shivendra. Questions related ICRB1. Shivendraj, we are having a different session on YouTube that is completely ICRB and ISRO. Okay, so you can take that session as well. This yesterday also I had that session. Monday also, I think, yeah, Monday also I had that session. So you can check this on the YouTube channel of IGC. Okay, here I try to cover gate type questions. Okay, because ICRB questions are much simpler. It's like one line question, concept based questions. Okay, so if I bring those questions, then I mean, we can do that, but basically, if we have to build concept, we have to solve a little difficult type questions. Okay, like gate questions where you apply like more than one concept. Okay, chalo. So yes, thank you guys. I'll see you next week. Okay, thank you.